Welcome to the Merlin and Metro News Network. Today's program begins our coverage of the flight control systems. We'll begin with the rudder and aileron systems discussed in this tape. These systems, like most of the flight control systems, are mechanical, and as such, mechanics usually find them easy to inspect and repair. They are, however, absolutely essential to the safety of the aircraft, the aileron control system especially. Now let's roll our first program.
The rudder and aileron flight control systems are mechanically operated through pilot actions. Rudder pedal assemblies are installed in front of each pilot. Standard flight control cable is used to transmit pilot and co-pilot inputs to a bell crank installed at the bottom of a rudder torque tube. The ailerons are controlled through the rotation of the control wheels. Sprockets installed on the shaft connected to each wheel transmit motion through a chain that runs through the control column. From here, it connects to standard control cables that are routed aft to an aileron bow tie. The bow tie rotates an aileron torque tube that is in turn connected to two push-pull tubes. Through a series of push-pull tubes and pivots, motion is transmitted to an aileron bell crank located in front of each aileron. A push-pull tube connects the aileron and bell crank. Many similarities exist between the two systems. The rudder and ailerons themselves are attached to the aircraft through hinges. Each consists of hinge bearings mounted on a hinge support. In the case of the ailerons, these supports are bolted to the aft wing spar. In the case of the rudder, these supports are bolted to the vertical stabilizer spar. The aileron uses 3 of these assemblies. The rudder uses 2. The lower hinge point for the rudder is part of the rudder bell crank assembly. The control system in the cockpit is also similar. Each system allows both pilot and co-pilot input. Equal movement of both sets of controls is assured through the use of interconnects. In the case of the ailerons, the portion of the cable that runs between the control wheels is the interconnect cable. The push-pull tube that runs between the pilot's and co-pilot's rudder pedal bell cranks is referred to as the interconnect tube. In each case, one control cable attaches to each pilot's set of controls. The interconnects between each system provide equal control to each pilot. The cables connected to these control systems must be properly routed towards the rear of the aircraft. This is the path of the aileron cables as they travel aft. This is the path of the rudder cables as they travel aft. The rudder cables continue aft and connect directly to the rudder bow tie. The aileron force must change direction to reach the ailerons. This is accomplished through a bow tie assembly and aileron torque tube. A reinforced box-like structure is installed between the 2 fuselage frames located at the rear wing spar. A machined assembly is used to hold bearings to support the torque tube and bow tie rotation, and seals to prevent pressurization leaks. This unit is located within the box structure, which also provides a mounting point for the adjustable stops for the aileron bow tie. These stops determine the maximum allowable travel in each direction of the aileron system. Also working with the aileron bow tie is the aileron Gust lock system. This consists of a Gust lock pin with a spring-loaded plunger and Gust lock arm. A cable system will be used to pull the arm in this direction, which will force the pin farther into the housing. The plunger will compress until the next time the Gust lock hole in the bow tie aligns with the Gust lock housing. The plunger will then be inserted into the bow tie to lock it and prevent aileron movement due to wind gust. There is also a spring within the gust lock housing that will try to disengage the gust lock pin unless the cable system holds it securely engaged. This is a safety feature to ensure that the gust lock pin cannot inadvertently lock the bow tie. Beneath the fuselage, the torque tube connects to push-pull rods that run parallel to the aft spar. Swing links are located between the sets of push-pull rods. These units transmit motion outward until it reaches the aileron bell crank, sometimes referred to as the pork chop. This unit is used to convert the back and forth or left and right motion of the push-pull tubes to the up and down motion of the aileron. A short push-pull tube connects the aileron and the bell crank. The connection of this tube to the aileron is secured by a self-locking nut plate and must be further secured using safety wire. Rudder movement is controlled by the movement of the rudder pedals. The rudder pedals are supported on rotating castings, often called the rudder pedal hangers. Each hanger is mechanically connected to a rudder pedal bell crank, which are in turn connected together through a rudder pedal interconnect tube. The rudder cables are connected to the pilot's right rudder pedal hanger and the co-pilot's left rudder pedal hanger. The interconnect tube is what completes the loop between the two cable systems. If the interconnect tube is disconnected, remember that it will allow the rudder cables to go slack. If they are not properly blocked, the slack cables could foul on equipment or structures in some other part of the aircraft. This scenario can sometimes occur during nose wheel steering maintenance, since the pilot's rudder pedal bell crank has steering components installed on it and may be removed to facilitate maintenance. The rudder cables continue to travel aft through the fuselage. Along the way, they are supported by pulleys. As they reach the rear of the aircraft, they pass over another set of pulleys that is used to align them to the rudder bow tie. The bow tie itself is mounted on a hinge bracket located on the aft canted bulkhead. This bracket contains the adjustable stops to limit the rudder bow tie travel and provides a mounting for the rudder gust lock pin. It also serves as the lowermost rudder hinge point and bearing. A welded tube assembly is used to join the bottom of the rudder torque tube and the rudder bow tie. Part of this welded assembly is a flange that is used to engage the rudder gust lock pin. If the aircraft is equipped with a yaw damper system or an autopilot, the connection for rudder control will be made through an additional set of cable guides located on the rudder bow tie. Since the rudder torque tube penetrates the pressurized portion of the fuselage, it must be sealed. This is accomplished through an O-ring that is installed in a plate that attaches to the fuselage structure.
One of the major reasons for maintenance on the rudder system is caused by leaving the aircraft parked without the gust lock applied. If the blast from a jet hits the unlocked rudder, it will swing it around hard enough to damage the rudder torque tube, usually quite badly. A really strong gust of wind can accomplish the same thing. It's the sudden stop, not the force of the blast, that does the damage. In almost all cases, the rudder would not have been damaged at all if the gust lock had been applied. Keep the gust lock system in good working order and encourage crews to use it. Now let's return to our program.
The gust lock system is controlled by a handle installed in the pedestal. This handle is locked by detents in the pedestal to prevent uncommanded movement. When the handle is lifted and moved aft, two actions occur. The control cables attached to the handle are used to transmit motion to pull the rudder and aileron gust lock pins into place. This action also moves an elevator gust lock pin that is discussed in another program. The handle itself also contains stops that will prevent the power levers from being moved beyond the flight idle gate. This is necessary to prevent attempted takeoff with the gust lock engaged. It is also an in-flight safety feature, since the gust lock cannot be applied until the power levers have been moved below the flight idle gate. The aileron and rudder trim tab systems are also similar. Each is actuated by turning knobs located in the pedestal. These knobs contain mechanical capstan drums that are driven by the knob's rotation. Standard 1/16" flight control cable is wrapped from the center, around the drum, guided down through the pedestal, and aft to its respective actuator. Installed at each aileron and at the rudder are mechanical actuators connected to the respective trim tab. As the trim controls in the cockpit are rotated, the length of the trim tab actuator will change. Rigging is such that when the trim tab is faired with the surface, the actuator will be at its mid-travel, and the amount of cable wrapped on each side of the capstan drum will be equal. Since the trim cables must penetrate the pressure vessel, pressurization seals are installed at each exit point. These are rubber devices secured by 3 snap rings. If a cable must be removed, these seals must be removed first. Pulling a cable in fitting through one of these seals will destroy it. The trim tab actuators incorporate a set of internal and externally threaded shafts. One of these shafts is rotated while the other is attached to the control surface. Depending upon the direction of rotation, the total length of the shafts will change, becoming either longer or shorter. The threads on these shafts have been cut at such an angle as to be non-reversible. This means that even if the trim tab cable system were to become disconnected, force applied to the actuator by the tab itself could not cause rotation of these shafts. Attachment of the trim actuator to the trim tab is accomplished through the use of push-pull tubes. A single tube attaches the rudder tab to its actuator, while 2 separate tubes are used to attach each aileron tab. The geometry of this attachment also varies between the aileron and rudder. The aileron tabs are also used as servo tabs to reduce aileron control forces. Because of the angle at which the push-pull tubes mount to the tab will deflect in the opposite direction from the aileron as the aileron moves. If, for example, the aileron is moving up, the tab will deflect down. This angle and direction of this deflection has been designed to generate an aerodynamic force that will assist the pilot in moving the aileron. This is an inherent design feature, and there is no adjustment for this action. Due to the lower amount of force required to move the rudder, it does not feature servo tab action. Adjustable stops are installed on the trim cables themselves. The aileron trim stops are located in the left-hand flap well. The stops for the rudder trim system are located under the center aisle area of the cargo compartment, so that the pilot can easily determine the amount of trim tab displacement. Indicators are installed in the control knobs themselves. These indicators are attached to shafts that extend through the basic capstan assembly. Gears are used to connect the indicator to the capstan. Since full stop-to-stop travel of either the aileron or rudder trim tab requires many complete rotations of the control knob, the indicator travel is slowed down through the use of gearing to provide a total travel indication. Like almost all flight controls, the rudder and ailerons feature mass balancing. In the case of the rudder, This consists of a large lead weight that is bolted to the rudder structure that extends forward of the hinge line. The ailerons are balanced by weights that are bolted to the aileron structure, located forward of the hinge line. There are limits set forth in the maintenance manual that define the balance range for each of these surfaces. Other than to inspect that the weights are still securely in place, control surface balance is not an item of routine maintenance. It is, however, absolutely critical that after painting or repairs to a control surface, that the balance of the affected surfaces be rechecked and adjusted as necessary. A more complete discussion of flight control balancing is contained in the Flight Control's Maintenance Practices tape.
Well, that covers the rudder and aileron system. Our next programs will cover the elevator and flap systems and one of all our favorites, the SAS system. Until then, good flying and good maintenance.